Now, as you can tell from the title on the screen, we're back to exponential functions after our long interlude into logarithmic functions. And the first thing we want to do is talk about solving exponential equations. So, first thing I want to do here is recall something to you about the difference between exponential functions and power functions, because they're fundamentally different. And then we'll talk about the techniques we'll use in solving exponential equations. Recall, there's a fundamental difference. A fundamental difference. I want to make sure you're very clear on this, between, and I'll do this with an example to make my point clear, between x cubed and, let's divide the page into two parts, 3 to the x. Well, the first obvious difference is that over here we have a situation where we have a variable to a constant power, and exactly the opposite here, we have a constant to a variable power. Okay, well, those are the obvious differences. The important thing for us in solving equations is going to be to undo these various things, these various functions. How is the x cubed function undone? It is undone by its inverse function, which is the cube root of x. And that is its inverse function. Whereas for 3 to the x, which is what we've been studying in this unit, the exponential type function, this is undone by a function that looks entirely different, log base 3 of x. And this is the inverse function here. So don't confuse what you know about powers with what you have just learned about exponentials in this unit. Okay, it's very important to keep these separate. Undoing an exponential power is to be done using a logarithmic function. Now, we've seen this before, but I thought it was worthwhile making the point again. Okay, now I want to talk about solving exponential equations, and I'm going to do 5 examples for you. We'll start easy and work up to the complicated ones and get a few graphs in here. So here's the easiest one of all. Solve for x. 3 to the x plus 1 equals 81. Now, the easiest way to do this one, you can apply the techniques we'll learn later, but the easiest way to do this is to use your powers of recognition and recognize that 81 is just 3 to the 4th power. So, what happens to the equation? It is now 3 to the x plus 1 equals 3 to the 4th power. Well, we can unexponentiate this, undo the exponential function by doing the log function, and I'll write it this way, hit with log base 3 of box. Okay? And having done that, we get x plus 1 equals 4, and then that makes x is equal to 3. So there we are, and you can check this on your own. I'll leave that to you. But it's quite easy, and if you recognize the power, that 81 equals 3 to the 4th, you're home free on this one. Here's the second of my 5 examples. Solve for x. E to the minus x squared power equals e to the x quantity squared times 1 over e cubed. And I wish to solve for x here. Well, the first thing I'm going to do is simplify. The left-hand side is fine, e to the minus x squared. The right-hand side, this is e to the x quantity squared, that's e to the 2x, times e to the 3 on the bottom is e to the minus 3, and so I can add those up there. And I end up with e to the 2x minus 3 using my exponential rules that I know. And so now you know what I'm going to do. Since the base is the same on both sides, I'm going to hit it with a log, and in this case it's the natural log, because the natural log has base e corresponding to the base e here. And I'm left with minus x squared equals 2x minus 3. And really, that's the end of the exponential part of this equation. Now it's just a matter of solving this as a quadratic. Of course, there is a problem you have to keep in mind, that I solve this now, and in the end I'm going to get some numbers which I really should check back in the original equation, because there may be extraneous solutions, so you want to be careful about that. But let's go ahead and do this. Put the minus x squared over on the right, so I have 0 equals x squared plus 2x minus 3. Again, I have the luck of the course, and I have x plus 3 times x minus 1 in my factoring here. And therefore, x is equal to minus 3, or x is equal to 1, the numbers that make these two 0. And if you check, I'll leave that to you. The check is left to you. But if you check, you'll see that both of these numbers work. So this was mildly more complicated than the other one, mostly in using the exponential rules at the beginning and then hitting it with natural log. Now let's up the difficulty and look at this case. You'll have lots of chance to practice these. Solve for x. 4 to the x minus 2 to the x minus 12 equals 0. Well, this may bother you at first because although I have exponentials in here, they have different bases. Luckily, however, the bases are related because 4 is just this base, 2, squared. Well, if you observe that, then you observe that since 4 to the x is 2 squared to the x, if I switch the order of the 2 and the x, I have 2 to the x quantity squared. Since that's true, we now see that this is an expression that we've seen before. This is called quadratic in form. So, since it's a quadratic in form, we treat it just like a quadratic, and we solve. So let me first write it. So this is 2 to the x quantity squared, as we saw, minus 2 to the x minus 12 equals 0. This is quadratic in form because the 2 to the x in this problem acts like the x did in a regular quadratic. So we can go ahead and try any technique we want. Turns out this factors very nicely into 2 to the x minus 4 times 2 to the x plus 3 equals 0. And then, of course, the factors, each of them might possibly be 0, so that means 2 to the x could be 4, or 2 to the x could be minus 3, and we'll look at those two different cases. Well, 2 to the x equals 4, you don't need to do anything difficult here. You can apply the log rule, log base 2, to undo the exponential. But why bother? It's easy to see that there's only one solution here, x equals 2. So that's more recognition than it is using log rules. Over here, however, we recognize immediately that this is impossible. Why is that? Because 2 to the x is always positive. If you remember the graph or you remember the function, taking 2 to a power is always positive. It can never be negative. So therefore, this is the only solution, and the check I will leave to you. You can go ahead and see that it works here, and that's the end of this particular problem. So the important point here is that we ended up with something that was quadratic in form, and we also have to recognize that 2 to the x cannot be negative. Here's one, solve for x. 5 to the x minus 2 is equal to 3 to the 3x plus 2. Again, notice the bases are different. So the solution here, these bases are different, and they're not as nice as the other one where we had 2 and 4 was 2 squared. 5 and 3 don't have any relationship like that. So what I'm going to do is just ignore the bases and hit with the natural log of box. Because the bases are different, all I want to do is get the x's downward, and any log will do. Natural log, of course, is the one I will always choose. So doing that, I get natural log of 5 to the x minus 2 here equals natural log of 3 to the 3x plus 2. So I simply natural log both sides. And now I use what I know about powers. The power x minus 2 will come down using the log rule, and the power 3x plus 2 will come down. So I have x minus 2 times the natural log of 5 equals 3x plus 2 times the natural log of 3. And now everything's on one line, and the natural logs you see only appear as constants. So this is just a linear expression in x. So I just gather my x's together and solve for x. So let's see, I'll multiply out both sides. I have x times log 5 minus 2 times log 5 is equal to 3x times log 3 plus 2 log 3. And let's see, I will bring my x over to here and then bring my constant over to the left. And what do I have here? I'll have minus 2 log 5, which was already there, minus 2 log 3, which has been brought over. And I have 3x log 3, which was already on the right, and I've brought over minus x log 5. And over here I will combine, I will pull out the x, because that's what I'm looking for after all. I'm left with 3 log 3 minus log 5. And on this side I'll pull out the minus 2 just for convenience, log 5 minus log 3. And then with one step, which takes me to another page here unfortunately, one step, actually I can slip that in down here. Let me go ahead and leave that. X will be equal to this side over this side. So it will be minus 2 times log of 5 minus log of 3. Could be rewritten if I wanted to. I don't think I'm going to bother doing it. So I'll write minus log 5 minus log 3. I could have written log 5 minus log 3 as log 5 over 3 because of the difference. And actually, that should be a plus, shouldn't it? I subtracted a minus out, took a minus out, I should have a plus here. So that's plus. I could make that into 15, but I won't. And this will be 3 log 3 minus log 5 down here. I'm not going to go to the other page. And then I approximate this in my calculator, and I get minus 3.21. So there we go. That finishes off that problem. Got a little jammed here at the bottom. But all I did, once you have a linear, once you recognize it's linear way back here, all the rest of this is very common calculation that we've done many times before. Okay. Well, I have a final example now. And this one I'll go ahead and show you a graph also, and you'll find out I have to. Example. Here's my final example. Solve for x. X plus e to the x equals 2. X plus e to the x equals 2. Well, I'm going to go ahead and in my solution I'm going to try the same kind of thing I've done before. I want to get, among other things, I'd like to get that x, which is exponentiated up here, downward. So why don't I try and do that? X plus e to the x equals 2. I first isolate that. E to the x is 2 minus x. Then I hit it with the natural log function because that's the base e. And that'll give me x here equals natural log of 2 minus x. And guess what? I'm no better off than I was before. Previously I had an x that was upstairs. Now I have an x that is within the natural log. If I try to undo this to get the natural log out, I'm just going to be back where I am. So the point is, I've reached the stage where I can't seem to get any further algebraically. Doesn't seem to be any help. And you will reach equations that have this property, and this is one of them. There's nothing you can do algebraically. However, then we can resort to a graphical imagery. Let's see, x plus e to the x equals 2. Rewrite that as x plus e to the x minus 2 equals 0. Call that the function f of x, and then graph that. If you do so, and I did so on the window 0, 1 by minus 1, 1, and I got a picture here that looked more or less like this. There's one axis, the other axis. The picture looks something like this, and where it crossed was approximately 0.44. And although that's an approximate solution, approximately 0.44, which may not be altogether satisfactory to you, it is the only solution that I can get in this case. So, with that note, it's time for us to stop looking at equations, for you to work some of these on your own. When I come back, we'll talk about exponential models. And now, as the final segment of this unit on logarithmic and exponential functions, we'll look at exponential models. And the two models we'll look at are compounded interest and the model for growth and decay, both of which are very commonly used. Okay, for exponential models, we'll start with number one, compounded interest. Now, we've talked about interest before, which is the reason I've written all of this out. I want to recall that P stands for the initial principal, the money that you start out putting into your savings account, for example. R is the interest rate per year that you are going to be awarded by the bank. N is the number of times calculated or compounded per year. The number of times what is calculated? The interest. Now, in the previous problems, we've only looked at interest rate calculated once a year, at the end of the year. Now we're going to look at cases where you calculate several different times throughout the year. And if you do it over a period of t years, of course, you have n per year times t year. You have nt, the number of times compounded in t years. And then finally, at the end of any given time, say a year, we'll look at the amount, and we'll use A for that letter. Okay, and just to make sure you understand what I'm talking about when I talk about compounding or calculating the rate at several times over the year, let me draw you a little bit of a picture here, just to make sure that the idea is clear. And I'll use, say, the n equal 4 case, although it doesn't matter what case I use. And here's the picture. Imagine, if you will, that this is the year, a year. Okay, it'll be the same for every year. This is 1 year of time, going from back here all the way out to here. And let's imagine that the year, n equal 4 is the case I'm looking at, has been divided into 4, usually referred to as quarters. So that would be 3 months each, 4 quarters. Now let's imagine that over the course of this year, you have a yearly rate of interest, and that rate of interest is R. Okay, that would be if you computed the interest once at the end of the year, having begun with a principal P and ending up once with whatever you get at the end with this interest based on that principal P added. Now, when you compound it at these various quarters, what you're doing is you're using R over 4 to compound the interest up to this point, another R over 4 when you compound it at the second quarter, another R over 4 when you compound it at the third, and the same thing when you compound it at the fourth. So that's how that works. The compounding, if it's broken up 4 times, or 5 times, or daily, or secondly, or even, as we'll find out later, continuously, this is the basic idea going on. And you notice R over 4 plus R over 4 plus R over 4 plus R over 4, there being 4 of them, add to R. Okay, let's see if we can figure out the formula for what we'll have at any given time. And I'll do it this way. I'll draw a little chart. Here is the end of period blank, and I'll put in the blank below. And this is the amount, A, that you have at the end of that period. Okay? So at the end, for example, of period 0, when things begin, the only amount you have is P, your initial principal. Okay? At the end of the first period, now remember, period may or may not be a year. It may be a quarter, as in my previous page, or it may be some other time span. At the end of period P1, or end of period 1, what do you have? Well, you still have your initial principal, plus you have the interest that was gained on that principal. Now, how much interest is that? Well, it's the principal times you had R over the course of a year divided by how many times you've broken up the year. So if it was 4, it'd be R over 4. If it's 1, if you do it at the end of the year, it's R over 1. It's just plain R. But this is how much money you will have at the end of that year. Now, if you simplify this, you've got P times 1 plus R over N. And I'm going to note that it's to the 1 power, because that's going to have bearing in a minute. Okay, now let's look at the end of period 2. At the beginning of period 2, you start out with this amount. And then you go on to produce the same calculation. So you start out with P, 1 plus R over N, plus that same amount, 1 plus R over N, times r over n, because at the end of the year you take the initial amount you had and multiply it, or the end of the period, sorry, and you multiply it by r over n, the rate divided by however many periods there are. So this is what you have at the end of period 2. And if we do some algebra here, we see that p times 1 plus r over n is common here, so I can factor it out. P times 1 plus r over n. And what's left from here, I've got 1 plus in the middle and have r over n left over from here. Well, now I have 1 plus r over n twice, so I can write this as p times 1 plus r over n quantity squared. So now I think you begin to detect the pattern, and I could continue this. P times 1 plus r over n to the 1 occurs at the end of the first. P times 1 plus r over n to the 2 occurs at the end of the second. And the first one works out also, in case you wanted to check it. This is p times 1 plus r over n to the 0th power, because to the 0th power that's 1, which gives you back p. So the formula seems to be that if you're at the end of period nt, whatever year you're in, and whatever number period within that year, nt, the amount you will have will be a of t equals p times 1 plus r over n to the nt. That's how much you will have based on an argument that is developed from here. And this is the compound or compounded interest formula. Now this is opposed to the simple interest formula we saw before. This is the compounded interest formula. And we're talking about n periods per year. N periods per year, and we're talking about t years. Okay? This is the formula that one then derives. Now you might say, well, this is all well and good, but what does this have to do with exponential functions? Weren't we talking about exponential functions here? Well, you're quite right, and we need to go a little further to see that. And the question that leads to the exponential answer is, what happens to that amount that we saw on the previous page from the compounded interest formula? What happens to a of t as n goes to infinity? What does that mean? N going to infinity means continuous compounding. You're not compounding only at 4 times or 10 times or daily or secondly, but you're doing it continuously. That's where the number of times in a given year goes up to infinity. So the question is, what does the formula a of t look like if you let that n go to infinity? Well, we can see that very easily if we do a little rewriting. We'll take a of t, which from the previous page, remember, was p times 1 plus r over n, try and keep my r's and n's looking different here, times n to the nt power. And then I'll just rewrite this, and you'll see why I'm going through these motions. P times 1 plus 1 over n over r, so I'm flipping this fraction over, to the n over r power times rt. Now you see, inside all I did was flip the fraction over and write it as 1 over. Outside, if you multiply this out, the r's cancel and you have nt. Now why I'm doing this is a good question. I am now going to let h be equal to that n over r fraction. So continuing, I have p times 1 plus 1 over h, and up here I have h, and if I put the other power outside, I have rt on the outside. This is, of course, the same as what I had here. The n over r has been replaced by h, and I've just rewritten this. Now, this is in a form that should begin to ring a bell. Recall, when we talked about the natural exponential function, we talked about the development of the number e. Recall that as h here goes to infinity, 1 plus 1 over h to the h power goes to e. And h is n over r, so if n goes to infinity, as we asked up here, if n goes to infinity and the r is the rate, it doesn't change, then that forces h to go to infinity. So as h goes to infinity, 1 plus h to the h equals e, and that's the expression in here. So pulling this all together, we can now write down the formula, which is now an exponential function. So a of t is equal to the initial principal times e to the rt. And that is what's called continuous compounding. That's where you imagine you've compounded at every possible real number instant. And there's the exponential function I was promising here. So exponential functions have bearing in the business situation. Let me give a quick example here. Suppose your principal is $1,000, your initial principal. Suppose the rate is 10%, and remember that equals 0.10, and this will be continuous compounding. That tells me what the model is. And let's suppose the time period is 1 year. Well, then the amount at year's end is computed using this formula, and it's going to be A equals 1,000 times e to the 0.10 times 1, and that turns out to be approximately, in dollars, $1,105.17. Truncating again after the second decimal, which works out well for money. Just observe something about exponentials. The fact that the growth is probably bigger than you even expect. I think our intuition is not very good because of the drawings we often make. So my observation is that exponential growth, and here I'll look at the function y equals e to the x, but this is going to apply for others. Exponential growth is huge. Okay? It's really much more than you expect. So, let me go ahead and draw an axis system here, and I'll write some notes on this page. This will be the y-axis, which you can imagine being measured in centimeters for the purpose of this. This is the x-axis, also measured in centimeters. And let's just look at an exponential function, say this one. Now you know that this crosses here at 1, as they all do. And this is y equals e to the x. So e being bigger than 1 makes it one of the ones that goes up. Now this is an example of growth. And by the picture it doesn't look like it's very large, but that's deceptive. When you start putting in numbers, you realize just how deceptive. Here are the numbers I'm going to put in. 1, and the rest of these will not be to scale. They won't be in their right positions. I'm going to put in 1, I'm going to put in 6, put in 10, put in 24, and put in 43. Now 43 is not a very big number, but I'm going to put it in and see what kind of values I get as a y value representing growth here on this exponential curve. Okay, there are the points. And back here, the first one here, at 1 I get e to the 1, and e is about 3 centimeters, so that's not very big. Here I'm getting e to the 6th here, which is going to be approximately 220 meters, which is quite large, about the height of a building. And then e to the 10th, well, at that point we're getting extremely large. This is already, let's see, take that back. The previous one was 4 meters, sorry. This one here is about 220 meters. Get my numbers straight here. E to the 6th is about 4 meters. E to the 10th is about 220, and that's where we're at the height of a building. This one here, e to the 24th, is halfway to the moon. And that's quite a distance, and I've only gone up to 24. And finally, you go up to e to the 43. How far is that? That's approximately 4.3 light years. That's about the distance to the nearest star. And all you've done is gone to e to the 43. Now 43, as I said, is not a big number. So the point is that exponential growth is much, much larger than you realized based on the graphs we look at. Okay, speaking of growth, that is the second model I wanted to look at. and it comes hand in hand with decay. So growth and decay, exponential growth and decay. Here is the model, and I'll explain it. A of t equals a sub 0 times e to the kt. Now when you look at that, you should say to yourself, boy, that sure looks like that continuous compounding model. And if you did say that, you'd be right. It does. In the continuous compounding model, instead of this a sub 0, I had p, the principal. Instead of a k, I had r, which was the rate. But it was the same model. That's sort of the key here for exponential growth models. So a of t is the amount at time t of whatever it is we're talking about. A sub 0 is the initial amount, the amount you start with. And of course that means it's a of 0, which we also write as a sub 0, as usual. And the k is a real number, and we assume that it's not 0. So it's either positive or negative. If it were 0, of course, we just have e to the 0 here, which would be 1, and we just have a constant function, which is not very interesting. And what is this law called? This is actually referred to as the exponential law of, unlimited. Or sometimes you might say uninhibited. And it's either growth or decay, depending on what k is. It's in uninhibited or unlimited growth if k is greater than 0, and it's unlimited or uninhibited decay if k is less than 0. So the k is what determines the growth or the decay here. And I might point out that this exponential law is not very realistic, because frankly nothing grows or decays without limitations. Growth, for example, is limited by food available. It's also limited by space and other things. And decay is also limited. So be aware that there are other models out there. This is simply the simplest one. We'll start out with a couple of examples. First, we'll look at bacteria. And bacteria will be an example of exponential growth, even though we realize that usually they're in a dish and they're going to only grow until they run out of food. But let's imagine exponential growth and see what we're going to have. In this case, we'll let n be the number of bacteria at time t. Okay? So I'm using n now, and my model for this will look very familiar. It's n of t equals n sub 0 e to the kt, where in this case I can specify that my k is greater than 0 because I'm talking about growth. Now you should notice that again this is exactly the same model that was on the previous page. Instead of the letter a, I now have the letter n, which is what happens in practice. People choose the letters they like. And I have noted that k is fixed to be constant, greater than 0, so I actually have growth. Now, here's a question one might answer based on this. If the original amount of bacteria, if the original n sub 0 doubles, if you've watched it and you've seen it double in 3 hours, how long might it be until it triples? Okay, you've seen it double. Now you want to know how long will it be until it triples. Well, this will force us to answer a couple of questions and use the information that we've got. And this solution will mimic the kind of solutions that all of these exponential model problems will have. Again, let me write the model up here so I have it in front of me. N of t is n0 e to the kt. And notice that n sub 0 was not given to us. So we weren't told how much there was in the way of initial bacteria. Okay. In this, we will always want to find k. Okay, that's what we want to do. We will then use the given information to find k. We are given the following information. We know that it doubles in 3 hours, which is the amount will be 2 times the initial amount. This is where the word doubles gets used. That's where that 2 comes from. That will be, using the model again, we'll have 2 times the initial amount, when? When t is 3 hours. So the model says when t is 3 hours, we will have twice as much as we started with, that being n naught. So this is how I write down that in a mathematical sentence. Notice that not knowing n naught will have no bearing because it will simply divide out. So we will have 2 equals e to the 3k. I wish to get the e down, so I'll do the usual. I'll hit it with a log. I'll hit it with natural log, and I'll have natural log of 2 is equal to 3k. And then k will be natural log of 2 over 3. So I've found k, which is what I wanted to do. Now let me warn you, don't approximate yet. Okay? Hold off on that. We said way back at the beginning when we started talking about equations that if you have something in the equation that needs approximating, wait till the end and do one approximation for the whole solution. Don't do approximations along the way, because if you do, you'll be introducing errors and they can accumulate. Okay, what advantage do I have now that I know k? Well, instead of that generic model, I have now made it more specific to my particular problem. I know that my particular model is n of t equals n sub 0 times e to, I know the k, natural log of 2 over 3 times t. Okay, that's my specific model for this specific problem. Okay, so my question was, when will it triple? So I want to know when triples happens. Well, that will happen when I end up with 3 times the amount I started with, 3 times n sub 0. That will be when. I don't know when, which means the variable I'll be looking for here is t, the time that makes the tripling happen. And again, not knowing n naught is really no difference, because that will divide out again. Well, we have 3 is equal to e to the log 2 over 3t. Again, I will hit this with a log, hit it with the natural log. I'll have natural log of 3 equals the exponent, which is natural log of 2 over 3t. And now I solve for t, and that's easy. I get that t is equal to 3 log 3 over log 2. There's no rule for a quotient of logs, so don't think you can simplify this. And then I approximate it to be 4.75 hours. And so I now know that if it took 3 hours for it to double, that it'll take 4.75 hours total to triple. And if I wanted the difference between the doubling and the tripling time, I could take the 3 hours away from this, and I'd know there'd be an additional 1.75 hours before it tripled. We want to now look at one that's an example of decay. And the example that's commonly looked at, and I'll look at it here, is radioactive decay. Okay? And I will use A to stand for the amount of material, whatever the radioactive material is, of material present at time t. So instead of looking at the number of bacteria, we're looking at the amount of material. The model will be the same model we've used throughout. We're back to the letter A now, so A of t will be A sub 0 e to the kt. And in this case, since we're talking about decay, we know that k is less than 0, negative number. There is one definition I want to make before I state the problem I want to look at. This is a definition for something called half-life. This is very commonly used in the radioactive decay world. Half-life is a time. It is the time required for half the material to decay. Now, you have to realize what's happening with radioactive material. Radioactive material is tossing off little pieces of itself. Those alpha particles, those beta particles, and even the gamma waves are removing parts of the amount of radioactive material you start with, so after a given amount of time, there'll be less of it left. The time required for half the material to decay is called the half-life of the material. Okay, with that in mind, I'm going to pose to you now a problem. You've seen me solve at least one of these using bacteria, but I'm telling you that the solution there is the same solution technique that you'll use here. So let me give you an example to ponder and struggle a little bit with, and then I'll come back and show you what I would have done. And here is the example. If the half-life, which we just defined, of a material called carbon-14, carbon-14 is a radioactive form of carbon. We all have it in our bodies, much less than we have carbon-12, the usual form of carbon, but we have carbon-14 in us. Let's suppose the half-life is known to be 5,600 years. And what has happened is that wood from a tree has been dug up at some archaeological site containing only 1.67% of its original amount of carbon-14. The question is, when was the tree buried? Now, how does this carbon-14 dating, which is what we're talking about here, work? The basic idea is the following. All living bodies contain carbon-14 as well as carbon-12. When the body dies and is, say, buried, or when a tree dies and is buried, then the carbon-12 remains, but the carbon-14 is radioactive, and so it decays away and eventually disappears. So by figuring out how much of the original carbon-14 is left, we can then estimate how old the tree, in this case the wood from the tree, is, and find out, therefore, when it was buried. So the model we're using here is, just to remind you, A of t is A sub 0, the initial amount. And we don't know that, but as you know, it probably won't matter, and e to the kt. So think about this a little bit, and I'll come back and show you what I did. Well, I hope you gave this a good try. And here's the problem again. If the half-life of carbon-14 is 5,600 years, and wood from a tree has been dug up, which contains only 1.67% of its original amount of carbon-14, when was the tree buried? Well, here's how I would begin the solution. First thing, as always, is to write the model down. I wrote it down there for you. A of t equals A sub 0 e to the kt. Now realize that A sub 0 is unknown, but as we've seen in the previous example, that probably will not matter. Okay, what do we want? We want to find k, because then we'll have a specific model for this specific problem. Now we are given the following carbon-14 information. Given carbon-14 info, we are told that 1/2 of any original amount, 1/2, this is the word half in half-life, the 1/2 is equal to A sub 0 times e to the k 5,600, because that was the time in years that it took to get 1/2 of what you originally had. Remember, we're decaying here, so you have less after a given amount of time. This was the half-life statement. Well, from the half-life statement, we can solve for k. Notice that the A0 is common to both sides, and we'll divide out. I am left with 1/2 equals e to the 5,600k. Again, I do the same thing. I'm going to hit this with the natural log to undo the exponential. I will have natural log of 1/2 here equals 5,600k. And then I can solve for k and easily get k is equal to natural log of 1/2 over 5,600. And you may remember natural log of 1/2 can be rewritten as minus log 2 over 5,600. And there's my k value. I will not approximate it, because I know that that may lead to error later. And I will also note that, thankfully, it's a negative number like it's supposed to be. Log 2 is indeed positive, so this is a legitimate negative number, so we are talking about decay. Okay, well, now I have k. Now I have a specific model. See, before I had a generic model for this type of problem. Now I have a specific one where I've used the information to get a specific k. A of t is A sub 0 times e to the minus log 2 over 5,600 all times t. So, now I use the information from the problem to answer the question. I know that I have 1.67% of the original amount of carbon-14 remaining, and I want to know what time it took to get to that stage. So the 1.67% translates into 0.0167 of A sub 0, right? That's how much I have of the original amount of carbon-14 in the piece of wood. That, by the formula here, my model, is A0 e to the minus log 2 5600 t. And I want to solve for t here. I know that the a-naughts will divide each other out, so I have the t as the only variable to solve for. So I have 0.0167 equals e to this very large exponent once again, minus log 2 over 5600 t. And then I do what I have been doing. I hit it with log. And I have natural log of 0.0167 equals minus log 2 over 5600 all times t. And so finally, t is equal to minus 5600 natural log of 0.0167 all over minus log 2. Okay, I think, well, I put the minus on top. I don't need it in both places. And that is approximately, if you really abbreviate it, 33,000 years ago. So that's how carbon-14 dating works. It is based on an exponential model. And that exponential model finishes this segment. It also finishes Unit 5. We've now finished talking about exponential functions and logarithmic functions. And now we'll move on to Unit 6, which is an entirely different topic.